Amazing. Thank you all for your patience. And I am Ibukun, and I'm an engagement manager at Faculty. We are one of the world's leading decision intelligence providers. Basically, we help our customers make better decisions, okay? With me today, I've got Kat, I've got Christian from Faculty. I've also got Laird and Kiron from Springer. Now, in today's digital world, content is king, right? But merely maximizing the volume of content is not sufficient enough. And so we need to go beyond and focus on driving engagement, because that's what's truly going to capture the attention of our audience. Now, we've titled this talk, Maybe Content is Enough, with a nice touch on ensuring we're protecting user privacy, okay? And in the next 38 minutes, what we're going to do is we're going to start with talking about the business. I'm going to let Laird and Kiron, of course, introduce Springer Nature. We would then proceed to the data science, which is the science behind the contextual multi-armed bandit. Kat is obviously going to come on as well to bring this more to life. We will then proceed to the system. Christian is going to come on and talk about how we've been able to keep things fast. We have some time at the end for Q&A, so obviously, given the time we've spent already, we'll just make sure that we give you the time to ask the right questions you have, okay? Cool. I will now be introducing Laird, who will cover the business.
Thank you, Ibukun. Hopefully you can hear me okay. I'm Laird. I'm one of the product managers at Springer Nature. And I can just advance these slides by pressing this button. Okay, lovely. So I'll just very briefly introduce you to Springer Nature and the problem we've worked on with Faculty. Springer Nature is a large academic global publisher. We publish over 3,000 journals, academic journals. We have over 1 million articles submitted to us every year by researchers. We publish about 350,000 of those articles. We also publish about 13,000 books each year, and we publish those across a number of different imprints, some of which you may possibly have heard of before. One of them is Nature, under which we publish the journal Nature. There's also Springer, Biomed Central, Scientific American. It's also worth noting that there are over 1 billion downloads from our big content delivery platforms. Those are downloads of articles and chapters, and those big content delivery platforms are nature.com and SpringerLink. Next slide. So the problem that we worked on with Faculty. So one issue that our end users, researchers face, and maybe some people in the audience face, is that there is an increasing volume of research outputs published every year. So just for some numbers, there were 14 million new metadata records registered to Crossref. So Crossref is essentially kind of like the official registry for digital object identifiers in the industry. And so there are 14 new records published, and those represent things like articles and chapters, for example. And the number of research articles being published every year is increasing somewhere between sort of 8 and 9% every year. So there's sort of like this deluge, and that's just some of the research outputs. And so there's this deluge of research outputs. It can be a problem for some researchers. It's hard to find what's relevant to you and to keep up in your field. And then from the Springer Nature commercial side, we still make most of our revenue via B2B2C business model, in which we sell subscriptions to the content that we publish to academic institutions like university libraries, for example. And then researchers at those institutions come and access the content on our websites via their institution subscriptions, often proving their institutional affiliation to do so via things like IP address, for example. And every year when we go back to librarians, they always want to know, well, have researchers actually been using this content to make a decision about whether they want to renew and continue to pay us access to that content? And so every year we want to drive more and more usage of the content on our websites to be able to maintain those revenues. And so one way that we can address both the need of the researcher to find what's relevant to them and also sort of keep them on our websites reading content is by providing relevant content recommendations, and that's what we've worked on with faculty. My colleague Kiron will tell you a little bit about some of the challenges of doing that now and what we've done.
Thank you, Laird. Great. Okay, so I'm just going to talk about a few more of the unique challenges that we had when it comes to presenting recommendations to readers. So, as Laird says, we've got a couple of big content platforms, nature.com and SpringerLink, and when they come to the site, we don't know who they are. Okay, they've got several objectives, and we're not sure what that is. So they could be wanting to learn about a new topic. They might want to be staying up to date in their field. They may want to dig deeper into the research, like look at the reference lists, the data, the figure, et cetera, et cetera. And we never know. And partly, as Laird mentioned earlier, it's because of the business model. Users don't need to sign in. They don't, and also institutions are very wary of privacy, as users are as well. So we can't personalize the experience. And that has led to us creating some models, or having to create some recommendation models that use the content that they're coming to see rather than their behavior and personal data. And that's what we've done with faculty. And that was one of the challenges around privacy. But also, researchers want relevant recommendations. They don't want recommendations that they may have read already, seminal papers necessarily. They also, we also have a reputation to uphold as well. We don't want to present irrelevant, spurious recommendations that could harm our reputation. And that's another reason. Another reason around reputation is some of the UX work that we did. So it's not just the relevance that would harm the reputation, it's actually the user experience. So here you can see on the right-hand side, this is a Nature article, and it's the experience that we created. And when we started working with faculty, we took a step back and we looked at our recommendations previously, and they hadn't performed well. They had got less than 1% engagement, and that was because they are in blind spots. They're either on the right-hand side of the page, which is a blind spot to readers that we're aware of, or they're at the bottom of the page, and we got low engagement. So when we started working with faculty, we thought, well, we looked at the engagement metrics, and 15% of our users, they bounce immediately. 20% they download the PDF, so they come to read an article and then they download the PDF. But about 65% of them actually spend some time engaging with the article. They're there to evaluate it, to see if it's relevant, assessing the abstract, the references, the figures, etc., etc. So then we thought, well, how can we present recommendations at the right time that doesn't disturb their reading journey? They're primarily there to read the content that they came onto the site to read. But how can we present it at the right time that doesn't annoy them, that doesn't get in the way of their primary task? So we had a hypothesis that if we present recommendations either when they've downloaded the PDF or after 20 seconds and they'd got to the bottom of the page of the reference list. And to us, we felt there were indications that they'd completed their task, that they'd assessed it and got something relevant, and they'd be open to a recommendation. And that's what we did. So that was the UX work that we did in product work while faculty were building the early models. And what we did to test the designs was that we put our citation API that we had already of ours, one that we had built which hadn't performed so well, into the designs. And just the designs alone increased engagement by 320%. So it was a huge success. And then when faculty's models were ready, the engagement was even better. So what we did was we've created a recommendation system that consists of 2 individual unique recommendation systems that serve different needs, with the contextual multi-arm bandit selecting which recommender to serve. And the impact has been over doubling the engagement once again. And that's because faculty's models had much higher click-through rate than ours, so the recommendations were more relevant than our citation API. But as well as that, their systems have been able to expand the coverage. So our systems could only present recommendations at 62% of articles, but theirs is 98%. So with increased coverage, increased click-through rate, it's doubled the impact as well. So it's been a huge success. And just finally, in production, what we've got now is the recommendation system on nature.com and SpringerLink, and we're also working to expand the content types and potentially thinking about expanding languages as well. So it's been a great success, a good combination of UX design, products, and data science work. And on that note, I'm going to pass over to Ibukun to talk a bit more about the data science. So thanks.
Thanks, Kiron. Cool. sure you're all thinking, how did we do this? What's the science behind it? For me to break down the real, or the concept behind the contextual multi-armed bandit, I'm going to do it in 3 steps, okay? I'm going to start with the first step, which is the one-armed bandit. I don't know how many of you have been to those game shops where you've got the big slot machine, and then you obviously, exactly, that's it. You put something in, and you either get a payout or you don't. It's quite simple, nothing too exciting about this. The next step is the multi-arm bandits. Now, I want you to imagine more than one of these machines. So 3 machines, for example, at once. And what you're really trying to do here is you're trying to select the best machine to give you the highest payout. Basically, you're trying to increase your winnings or reduce your losses, right? And so there is a world here where the concept of exploration and exploitation comes in, right? With exploration, obviously, when you start with imagine 3 machines at once, you're not sure which machine will give you the best payout, right? You're gonna start maybe putting in different inputs, sorting money, trying whatever, and the time you spend between when you start with your first input into the machine and getting out the first reward, you've lost some time between that, right? That's exploration. And exploitation happens, of course, when you select or when you find the machine that's just right for you, that gives you the earnings or the winnings that you're after. How does this all fit in with bandits? Now, I want you to imagine a world where let's add in a little bit of a layer of complexity here. Context, right? Now imagine, right? We've talked about the one slot machine or one-armed bandit. We've talked about having multiple machines, right? Exploration versus exploitation. And now we're talking about the next step, which is context. It could be days of the week, for example. So maybe on Monday, machine 3 would give you the highest earnings, right? On Tuesday, machine 2 gives you the highest earnings. But you don't know that, okay? In the context of Springer, we obviously have and I'll bring it to life in a moment. We have users that go onto the website, and remember, we're trying to protect their user, their privacy here. We don't know a lot about them. In fact, we know nothing about them. We only know about the features and the context that we've put into our reinforcement learning model. Now, what happens here, of course, is context in this choice is, like I mentioned earlier, features, which we put in terms of the article type, the article, I'd say the publisher, the type, the topic, etc. And what then happens, I'm just going to bring this to life in a moment, is to lift the veil, okay? So you've got your user, like I said, just let's imagine I'm a researcher, right? And I've gone on to nature.com to access an article. At the back of this, we obviously have our CMAPs, our contextual multi-arm bandit, and we've got different arms. In the context of this, we've represented our arms using different recommendation systems, right? I think in the case of Yahoo, they used, I think they used the different articles. So you kind of have 200 arms, and the bandit is basically trying to just imagine like a large, huge octopus trying to like find out which one is the best. And we obviously thought that wasn't the best solution because we're dealing with a search space of about 20 million articles. And you can obviously, quite chaotic to imagine 20 million arms. So we modeled the system using different recommendation systems as the arms, right? So I hope I've kind of explained what's going on there. And then the next step is then the CMAP selects which arm is actually, I guess, the best one based on what the article, based on the article that the user is reading. And so we have the CMAP there trying to obviously try out the exploration or exploitation, which one's best given the context at that time. And based on what is selected, let's assume here we've got 2 different arms, and the bandit has selected the second recommendation system. That selection is then fed right there into the model. and it outputs, of course, recommendation system 2. I'll talk about the systems in a bit, so let's just, I guess, look at it from a high level for now. And what happens there is when the model then feeds back the recommendations to the user. At the moment, we've got 9 slots, and I don't know if you remember the GIF that Kiron shared earlier. We've got 3 different recommendation slots per scroll, right? And based on what the user finds relevant at that moment, the user would either click on an article or download an article. I guess one thing to point out there is we obviously wanted to prevent clickbait, which is where, of course, you just like click, 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 get a reward, get a reward, get a reward. So what we fed into the system was a click and a download, right? And that's the way we've calculated our reward. So I think what happens there, of course, the behavior of the user selects which article is best for them, and then this is fed back to the bandit. And what then happens is the bandit learns over time which arm to serve based on, obviously, the context that's been fed to it. And the reward feeds back again to the bandit system on the top there. And it's a feedback loop. It goes over and over and over again. Like I said, when I call Kat up in a second, she'll bring it more to life with more, of course, more technical details. But just before I call Kat up, I thought it was worth just mentioning those 2 arms that I explained earlier, where I said Yahoo, obviously, they've got different articles, different arms, but we've decided on using our recommendation system as arms. I want you to imagine that I'm Kat. I am not Kat. Kat is sitting there. So let's imagine I'm Kat. I'm a PhD student, and I'm quite keen to understand articles related to my field of research, right? So what happens is I go on to nature.com, and I'm more interested in articles, either articles that are citing one another or similar articles, right? And so the contextual multi-arm bandit, the one I just walked through now, is able to denote my need at that point and feeds me recommendations from the first system, right? The first system here is a semantic similarity system, i.e. it feeds out, or rather the output it feeds out to the users is based on how similar articles are to each other, right? And of course, like I said, my need here is that I'm conducting deep research. I'm a PhD student, so I'd like to know more about a research area. Now, I want you to imagine that I am Jim. I am not Jim, but it's a weekend. I'm very interested in going through nature.com. I'm looking for trendy articles. So I'm not really interested in the depth. I'm just looking for interesting, exciting articles to read on nature.com. The contextual multi-arm bandit is able to learn this and says, okay, I'm going to feed Jim more output from recommendation system 2. The recommendation system 2 here is the topic model, right? So it basically feeds back to Jim trending articles, popular articles. And like I said, who is it for? People who are quite keen to stay up to date with what's happening in the development in the field. And before I hand over to Kat, I just thought it's worth shouting that when we built this, we obviously realized over time that the bandit was obviously leaning more towards the semantic similarity model, which is recsys 1, and less towards recsys 2. We obviously still saw some output feeding out from recsys 2, but we noticed that users click more on recommendation system 1, which is the semantic similarity. Cool, I'll hand over to Kat now, who'll bring this more to life.
Thanks, Ibukun. Hi everyone, hope you're having a good conference. Do I just press the arrow? Yeah, just wanted to check I'm not going to break it. Lovely, excellent. So I'm just going to talk very briefly on running some of these multi-arm bandits in the wild. So if you go into your books and you look at multi-arm bandits, you basically have this loop. So the agent makes a decision and takes an action. There's a reward associated with that action, and the agent receives that update, and it's great. And you keep going, and you keep going, and you keep going. But real systems often don't work like that. And in Springer and Nature.com, that definitely wasn't the case for a couple of reasons. The first is the frequency of the GA data update. So if you imagine an agent where every time it makes an action and gets a reward, it updates. That wasn't possible with the data. We had a lag with the data coming in. So what we ended up doing was we batched the rewards. So rather than the agent updating after every action, we would batch the rewards and then use that to do a larger, more meaningful update of the agent, which worked great. It's very cool. The other thing that allowed us to do was to parallelize agents. So if you imagine one poor little multi-armed bandit running all of nature.com, it's quite a lot of traffic to go through a single agent. So by batching the updates and making the updates, we also allowed us to parallelize our agents and meant that they could learn from each other collaboratively, and there'd be more of them, which was pretty cool. The second thing I just wanted to touch on briefly was like some of the great things you get from using a bandit, as well as just like learning what's a good system. And one of the big ones is that you can add additional arms into the system in the form of new recommenders. And I think, you know, this is something that we're talking with Nature, with the Springer guys a lot about, but it's really, really cool. So, you know, we can start to add new recommendations, new models into the system. The only thing really to note when you do that is to choose a sensible prior for the recommender. So, you know, make sure that it's going to get a good showing. You can say like clone a distribution of one of the other recommenders' rewards. And then you can monitor this. This is really cool because it maximizes the overall expected reward. There are 3 things that this means. So if it's rubbish, it won't be selected at all, which is great. A system that's generally bad but good in certain situations will be chosen less frequently. But what this means is, particularly in the context of a contextual multi-armed bandit, is like we can have different systems for different contexts. So if you're looking at mobile, if you're coming on the web, depending on how you landed on the article, and you can go through different systems. And this is actually extremely hard to set up in an A/B test. So yeah, that's it from me. I'm going to hand over to Christian.
Great, thank you very much. I'm going to try and compress this because obviously we've got less time. Engineering bring up the rear. So the system, so I'm Christian. I was engineering lead on this, so my job is basically to deal with data scientists who design something and figure out how to build it. So joy for me. I'm going to talk a bit about how we developed the system. I'm going to talk a bit like general overview and then some sort of interesting stories and hopefully some tips on anyone else who finds them in this space, particularly on Google or building a recommendation system. So I'm going to open with a bit of a hot take. In my career, I am of the belief that system design in machine learning is pretty poor. And I find that not only is this common in traditional software development, system design is really, really important, but in machine learning applications, systems design is almost as, if not equal to, as important as the modeling choices we make. And as a result of that, I'm going to talk a little bit kind of the system design decisions we made. And we've got a couple of sort of interesting metrics from the system design decisions we've made. So first one is recommendations are served well under 100 milliseconds for a recommendation system. That's quite fast, if I don't say so myself. We're able to serve 2.4 million recommendations a day for the price of under 40 euros a day. I'm going to be spending more in the pub tonight than that, so by all means come for a drink. And we've made some certain decisions that give us a system that has little to zero downtime. So we're able to guard against any training failures and inference failures and continue to serve recommendations in the system. I was going to give you the flow of our architecture, take a photo, conscious of time. I'll move on to some of the more interesting pieces. Or if anyone wants to talk to me after this, I'm more than happy to talk about it. I'll let all the cameras take the shots. So, what are some of the interesting things? So how do we keep it fast? So one of the interesting constraints for the project was that we needed to hit a target latency of under 100 milliseconds. So that presents a challenge. So the traditional model hosting architecture for any model is a training job, produces an artifact. We put that in some sort of version store that handles all the model versioning. We promote it to some production endpoint, and then we put an API in front of that, users send API requests over to it, and we start inferencing. problem we had with that was we were quite nervous. With 100 milliseconds to do everything, we wanted to remove all the compute out of inference that we could. So we decided to try and adopt a more of a batch-based system. And we could do that because we knew the entire document space. So we know every single document up front that we need to create a recommendation for. So one system design choice we said is let's leverage the ability to do that. So we have a model training job, and then we do a batch inference job off the back of that, and we compute every single recommendation every single day. Surprisingly cheap. We then write that to a NoSQL data store, and that gives us an advantage. So I don't know if anyone's kind of familiar with web development at all. They might recognize that NoSQL plus an API means fast, and we found that to be the same here as well. So we had an actual latency of thereabouts 50 milliseconds, which was pretty good. The other benefit is that we're able to guard against those failures. So once we've got recommendations in the data store, in production, fingers crossed we don't have a failure. If that failure happens, we have time to go and fix it, and any on-call engineers in the room would appreciate that, I imagine, so you don't have to get up at 3 in the morning and fix it. Next interesting, how do we keep it cheap? So faculty tends to leverage a lot of different serverless services. It's easy to deploy. I'm not going to give you the cloud pitch on this, but they're great. And generally we find they're a lot cheaper. So if you don't use your server, you rent a big box and you don't max it out, there's a bit of wastage in there. So in the context of this project, we use several services. So Vertex AI gives us access to pretty cheap training jobs, ML registries, Cloud Functions for Python runtime, really useful. Cloud Run, great service, I really like it. And my team in the corner will know that that's a big compliment coming from me because I'm a big critic of Google at times. But it's a great container runtime service, great for hosting APIs. And then you've got your sort of storage capabilities and BigQuery and data store, cheap, great, really good services. However, there's always a but when you design these things. So in the search for a sort of simple, and when I say simple, compared to things like Vertex that have very strong opinionations on what a training job should be, you must have an inference container when you commit a training job, even if you don't use it, that's great. So if you want to run a simple service that's long running, so longer than 60 minutes, and can have a GPU attached, bit of a challenge. So you might think if you do a bit of a Google search, there's GCP batch. But GCP batch isn't supported by Terraform. And if anyone's had the sort of joy of deploying services manually, that's not great. So if anyone knows any Google or Terraform engineers, wants to get that into their product backlog, that'd be great. So we decided to build our own. So we used a service called Workflows. Workflows is an orchestrator like step functions or Airflow. And we use that in conjunction with Compute Engine. So we start our own server in the cloud. We attach a GPU to it. We load our container. We run the workload. We wait for a callback. And then we shut it down ourselves. So we've had to create our own serverless service. And it's working really nicely. So we're able to sort of really keep particularly for our article embeddings, really cheap. And we're deploying this to different parts of the service as it's nice and easily deployable as well. And finally, one interesting choice we had to make because of cost and latency was to re-architect the bandit. So we had to build our own bandit. So traditionally, reinforcement learning algorithms follow the sort of paradigm of environment, observation, action, and reward. So there's a couple of bandits in packages you may know from Ray, RLib, and TensorFlow, but those all lend themselves to the traditional paradigm of reinforcement learning, i.e. online learning. That posed a problem for a couple of reasons. The main one being is the latency was outrageous. So I think one inference request was, 200 plus milliseconds. So there's no way we were going to be able to do that. So we decided to go build our own, and that has a couple of different advantages. So it's all written in NumPy, so it's nice and fast. However, the biggest advantage is following the sklearn paradigm of .fit and .predict. So by using .fit, we can offload training to offline training, which is great, nice and cheap. We can promote those bandit artifacts into our Cloud Run instance that scales. So we're able to sort of serve one version of a bandit, so we avoid the sort of federated and ensemble problem that can happen in these distributed systems. And yeah, it's very fast. Very, very conscious of time. I've got 1 minute left, so I will leave it there. Thank you very much. Any questions?
Right, I think they've done really well in managing their time after the startup, so we'll just take 1 or 2 quick questions if we can. Anybody?
So, because latency was a big issue, did you consider using, I mean, I'm assuming that's why it was a multi-arm bandit, but did you consider using any other coding frameworks like JAX?
Is it still on? Yep, okay. No, so faculty is mostly a Python development house. So a lot of our data scientists are only familiar with Python. The engineering team has a few other sort of interesting languages in the team, like Go and JavaScript. But generally, we try to stick with Python. The other consideration we have is when we build client applications, often we have to hand them off to other teams. And really, the sort of lowest bar for entry is Python. So, but yeah, I think we squeezed the juice on this one.
Okay, I think we'll move on to the next talk. I'm sure the team will be delighted to take any questions if you can find them around outside later. Okay, thanks again to them.